Howdy. When you make a telescope mirror, a paraboloidal telescope mirror, the mirror has a paraboloidal curve in it. And if you were to run a straight edge across there, right there is the sagitta. And it's how deep it is. And it's r squared over 2r, where r is the radius of curvature of the mirror, which is twice the focal length. And little r is the radius of the mirror. That's a little r. So, everybody knows all that, but the question now is, if you were to hog out a mirror, you have a volume of glass to remove, and it would be nice to know what that volume is. So if it were 1 cubic inch of glass to remove, that's a fairly small amount of work to do. But if you got a large telescope mirror, that might be 492 cubic inches of glass to remove. Be nice to know what you've got to remove so that you know what you're up against and how long it's going to take you to do it and such and such. So the question now is, what is the volume of the glass you're going to remove for a paraboloidal telescope mirror? And it is pi r to the fourth over 4r, where r is the radius of the mirror, and capital R is the radius of curvature, or twice the focal length of the mirror. So my goal right now is to verify this equation. One way to do it is with the disk method, and the other way to do it is the shell method. These are single variable integral calculus methods, and that's what we're going to do. So first of all, y equals ax squared is a parabola whose vertex is at the origin and it's opening up. Looks like that, where this is x and that's y. And another relationship is that a equals 1 over 4f, where f is the focal length. So like here's the directrix and here's the focus. Right there's the focal length. And the relationship between a and f is that combination right there. Back up to this guy, r equals 2f. So 1 over 4f is really 1 over 2r. So our equation for a parabola is y equals 1 over 2r x squared. So what we're going to do is we are going to revolve that about the y-axis. And so here we go. There's our parabola. We're going to revolve it about the y-axis to get this volume. And we're going to stack an infinite number of infinitely thin disks in here. So disc, all the way up. And there's some of their volumes will be that, some of that void in there. So let's take one of those disks out. There it is. Now, the volume of a disk is the volume of a cylinder, which is volume equals pi r squared h. And so there's h. And with respect to our equation, y equals 1 over 2r x squared, this will be a dy integral because it's thin vertically. And there is our r. And so to get our r, we need to write not y as a function of x, but x as a function of y. So if I were to swap sides, I would get 1 over 2r x squared equals y. If I were to multiply both sides by 2r, that would be x squared equals 2ry. And if I solve for x, I'd take the square root, and I'd get x equals root 2r root y. Or root 2ry. Okay, so we are going to sum up the pi r squareds, h's, And so that's going to be the sum of pi, and r is going to be this distance here for each disk, which will be root 2r root y, but then when I square it, that'll be 2ry. Then I got my h, which is dy. So if I were to sum these guys up, we're going to get 2 pi, and pull it out front with a constant multiple rule. I'm going to do an infinite Riemann sum, so it now becomes an integral of, I didn't pull my r out there, did I? Let's back up just a little bit. I can pull out 2 pi r with the constant multiple rule, leaving me the integral of y dy. We're going to do that from y equals 0 up to how high that is, which is going to be y equals r squared over 2r, the sagittal depth of that mirror. Alrighty. Well, that's going to be 2 pi r. The integral of y dy is y squared over 2, and it'll be evaluated from 0 to r squared over 2r. So I'm going to figure all this stuff up for r squared over 2r minus and figure all this stuff up for y equals 0. When y equals 0, this stuff is nothing, so I just need to do it with the r squared over 2r. So we get 2 pi r. Now r squared over 2r squared will be r to the 4th over 4r squared, and then that will be over 2. So, move my camera a little bit. The 2's cancel. I get pi r. I get an r to the 4th. And I get a 4r squared, an 8r squared downstairs. So that gives me a, I'm sorry. It was 4 because those 2's canceled out a minute ago, and I spaced that out. So I get a pi r to the 4th over, that r cancels one of those r's, so I'm left with 4r downstairs, and that is the sagittal volume of a paraboloidal telescope mirror using the disk method of volumes of solid revolution. Okay. As promised, we're also going to do that using the shell method. So here is our y equals 1 over 2rx squared. We'll revolve at about the y-axis. And I'm going to create a bunch of shells that goes from the function up to the top where it comes to a stop there. And that was because I go out r and I go up r squared over 2r. Now these shells look like that. I'm recording, but okay.
Oh, I'm sorry. You're taping?
I was.
Oh, shoot. Sorry.
Okay, give me a minute. I'm going to continue this here. I'm going to do that from a radius of nothing to a radius of r here. So if I take a razor blade and slice it right like that, I can open that bad boy up just like that. Stretch it out. And I have a box, and the volume of that box is length times width times height. So how thick is the box? Well, the thin aspect of this shell is horizontal, so that is a dx. The radius of that guy is x, because I'm going to do it from x equals 0 to r. So all the ones in between are x, and the radius is x, and the circumference is 2 pi x, so the length of this is 2 pi x. And the height of this would be the top of that, which is r squared over 2r, minus the bottom of that, which is x squared over 2r. So if I multiply length times width times height, I will get volume of that box equals 2 pi x r squared over 2r minus x squared over 2r dx. And so what I'm actually going to do for the volume is sum them up. So I'm going to do an infinite number of summations with infinitely thin dx's. So that turns into the integral. The 2 pi could move out front. Constant multiple rule. I'm left with r squared x over 2r minus x cubed over 2r. I've got a dx. I'm going to do it from x equals 0 to r, just like that. Okie dokie. So that's going to be 2 pi, the integral from 0 to r. The over 2r can move out front. You know what? I'm going to make a little bit more room here. Again, I got the 2 pi. I got the integral from 0 to r. The over 2r can come out, and the r squared can come out. Constant multiple rules, leaving me x dx minus 2 pi times the integral from 0 to r of over 2r of x cubed dx. I broke that into two integrals. Here we go. These integrals are really easy now. 2's cancel, so that gives me pi r squared over r times x squared over 2 from 0 to r minus 2. I got the 2's cancel, so that gives me pi over r. And the integral of this is x to the 4th over 4 from 0 to r. All right, here we go. I'm going to get pi r squared over r times r squared over 2 minus 0 minus pi over 4r times r to the 4th minus 0. And that gives us pi r to the 4th over 2r minus pi r to the 4th over 4r. Common denominator is 4, so if I multiply that by 2, I got to multiply that by 2. So I get 2 pi r to the 4th minus pi r to the 4th over 4r, which is, drumroll, pi r to the 4th over 4r. Again, we got the same thing. So let's try this. Let's take a fairly large mirror. Let's go 36-inch f3. So the focal length is 108 inches. So the radius of curvature is 216 inches. And the R is 18 inches. So the volume will be, well, I can't move my paper up there. Get out of the way, dude. Here we go. The volume will be pi r to the 4th over 4r, which is pi times 18 to the 4th over 4 times 216. All right, so I'm going to wimp out here, guys. TI-83. Okay, 18 to the 4th pi divided by parentheses 4 times 216, close parentheses, enter, and I am getting 381.7 inches cubed of glass to be removed. Let's look at more of a beginner mirror. 8-inch f5. The focal length is 40. Radius curvature is 80. Little r is 4. So the volume will be pi times 4 to the 4th all over 4 times 80. So 256 pi divided by 320 is 2.5 inches, cubic inches. Okay, I'm going to make sure I did that right because that actually sounds like more than I should have gotten. Here, let's see. I got pi, 4 to the 4th is 256, all over 4 times, what was r? Where's r? All right, there's r is 80. 320 is 256 pi over 3. Yeah, that's it. So can you see if you're used to making 8-inch f5s, it doesn't take you your entire lifetime to grind out your spherical or your paraboloidal evacuation of glass. But if your next mirror is a 36-inch f3 and you try to do it by hand, let's see, 381.7 divided by 2.5, that would take you 153 times longer to do than that one. So if it took you 2 days to do this would take you years to do. Of course, we do that with, mechanical tools when they have mirrors that big. But anyway, there we go. Volume equals pi r to the 4th over 4r sagittal volume, paraboloidal mirror. And thank you very much.